Jim Kunkel here. Make sure that you subscribe to my channel and set the notification bell to all so that you won't miss any of my new content. On this episode of Global Topic, it will be a discussion on corrosion engineering related to pipelines. Joining me today is Joe Pikas. Joe, welcome.
Well, thank you very much, Jim. I appreciate it.
Hey, I also failed to mention that Joe is with Technical Toolboxes. Joe, would you like to go through your background and explain a little bit about what you do in the industry?
Well, let me give you a background of it started like 54 years ago in 1966. Started with the pipeline company, worked there for 36 and a half years. Put one of the first 42-inch pipelines in the country. That was up in the Northeast. I was in engineering construction. I was in pipeline operations, corrosion control, pipeline integrity, risk, inline inspection, and you name it. And from there, I took an early retirement on my decision after 36 and a half years, and worked as a contractor through the industry, and wound up with Technical Toolboxes, who I've worked with even when I was with Williams Gas Pipeline Transco. And from there, my career has just kept going, and I expect it to keep going because we have a great industry.
Very impressive, very impressive. So, Joe, for the lay person who's watching this episode, who might only think that corrosion engineering is related to metal corrosion, as an overview, what else does corrosion engineering relate to? Well,
actually, it's deterioration of any material, and that includes metals and non-metals. And because of that, people don't think about it. But if you look at your plastics, your PE materials, polyethylene, we have problems even with the polyethylene materials that is used for pipe. They have cracking. We have ultraviolet degradation of materials. Just think about your automobile and the old vinyl roofs that they used to have, and any of the plastic materials that are in those. That's why we have sunshades to keep our steering wheels and the vinyls from deteriorating. So keep that in mind. And one thing we should think about is deterioration of materials is greater than 5% of the gross domestic product. People don't realize how much we lose each year, because of degradation or deterioration of materials. It occurs in, like I said, cars, trucks, buses, planes. We deal with this. You think of, just take, our airline structure. The wings exhibit stress corrosion cracking on them. And it's designed that way. Don't freak out. It's okay. And then you look at our equipment as cell phones, computers, electrical equipment, and then the infrastructure itself. Our highways, bridges, rails, water, sewage, gas, and then our nuke plants, our power plants, and refineries. The beat goes on, and then all of a sudden you could say, "Oh my gosh! Now I see where the 5% comes in." So these are the kind of things that we need to think about, when we're dealing with degradation of materials. And it's a natural. It's just like our skin. We could get sunburn. Well, so do materials sunburn too. So keep that in mind.
Professionals in the protective coatings industry have been strongly advocating that corrosion engineering be an important element during the design and engineering of infrastructure, such as, bridges, highway structures, refineries, pipelines, and other critical infrastructure. In your experience, why is it so critical that corrosion engineering be involved from the beginning in the design of an infrastructure asset?
Well, the first thing we should think about is paints and coatings should be the first line of defense to protect these materials. You could think about your house, the paint on your house. You could think of paint on the bridges. You could think of all of these. And the thing of it is we could be very easy on it, and we could say, you know what, we're going to paint, and we'll put a latex on it, and we'll paint it every year. Well, that's not very economical, is it? Whereas if we think about our infrastructure, we should be thinking about long term. We don't need to be painting every year. We need to do it in a way that we don't get any, and remember what we just talked about is deterioration of metal. Okay? And deterioration of metal is or the materials is our major concern. And if we get deterioration, guess what we have? We have failure. And that's the last thing what we want to see is failure of our bridges, failure of our infrastructure such as pipes and things of this nature. So we need to consider all of these things. And this is why the corrosion engineer, the coatings engineer need to sit down with the mechanical engineer, the civil engineer, or any engineer regarding design of structures. And that includes electronics too. So I kind of left that out in the overall things of thing, but we have to even consider our cell phones as part of that infrastructure too. So we don't want deterioration. Okay.
Yeah, pipelines are such a vital infrastructure in North America. So let's talk about fusion bonded epoxy, or as it's called, FBE. It's a coating that's used in the majority of buried oil and gas pipelines. What is FBE, and what are some of the most critical advantages and importantly disadvantages related to corrosion engineering?
Well, fusion bonded epoxy was developed back in the 60s as a savior to the pipeline industry because they felt it was going to be a coating that had all the qualities that we needed. It worked well against corrosion, and it also worked well with the cathodic protection that you usually need with it to for underground service. So we thought, wow, this is pretty cool because it was like a hand in glove type of scenario. And the FBE worked perfectly in that area. Well, however, as good as it is, there's always an Achilles heel to any product, any material. You just got to know where it is. Well, for years it worked out well, and with the hand in glove, and then all of a sudden, over time, we were putting our pipelines in AC corridors, and these AC corridors had an interference effect on the pipeline. So the best qualities of the fusion bonded epoxy, the little micropores, were supposed to allow cathodic protection. Well, those little micropores were a perfect storm for AC corrosion to occur. It's similar to bacteria. You could make the same analogy. Bacteria is set up in our micropores, what we're dealing with today at COVID-19. And these are the kind of same things that got into the FBE that created and actually an opposite issue with DC corrosion. And it occurred with AC. And so where do we have pipelines? We're trying to keep them all in the same corridors. And so this is the Achilles heel for the fusion bonded epoxy. So what we thought it was our savior turned out to be a little bit of a problem, and that was the Achilles heel. Now, the other thing too that occurred is we start developing high strength steels. Okay, what a great idea. They got higher toughness. They're resistant to cracking and things of this nature. And so, but we haven't kept up with since the high strength steels could be thinner wall. Well, they still corrode like the thicker steels, the older steels. So we didn't keep up with our FPE coatings for both the AC issues as well as the thinner wall high strength steels. We fix one area, but we need to go with the other area. Not that they weren't available. It's just that we kept using the same standards, and that's not a good thing. We need to move up as things change, and I'm calling that a paradigm shift that has occurred in the industry because of these issues. We really need to start thinking about the way Europe uses their coatings and the type of coatings. What they have is a 3-layer system, where compared to what we have is the fusion bonded epoxy for the most cases is a single layer, except in crossings. So this is where things begin to occur. So not only do we have problems as we changed the steels, made them tougher, we put the pipelines in these corridors, but then all of a sudden horizontal directional drilling come along, and so they were smart enough to make it 2-layer. Isn't that cool? Well, that was great because they put an abrasion resistant overcoat, and I think that's a fantastic idea, but they should have gone a little further, in my opinion, because we have to transport these pipelines on rail, on truck, and anything else, even on barges, and so we really need to have these coatings be also abrasion resistant, not just in an HDD crossing, but just in the mere transporting of these products and the movement of the pipe from one place to another. So these need to be considered too, and also the environment that it's in. So we need to start thinking more like the Europeans, using slightly different materials with the fusion bonded epoxy, and these are the kind of things that as industry changes, so should our specifications, our designs, and these are the kind of things that, in my opinion, need to be looked at a little closer, going back to the original design and sitting down with the mechanical, civil engineers, and electrical engineers. So this is my take on how we deal with all of this, and I think this is something that the industry needs to truly look at it, because we do need a paradigm shift. I think we're at the point that we need to look at these new issues that have been coming up.
Yeah, Joe, what a great conversation on corrosion engineering. Is there anything that we did not talk about that you would want to leave with the viewers of this episode?
Well, the key to all of this is not only the truly making our coatings what they should have been designed for, the first line of defense. We shouldn't be using other backups as the cathodic protection as now beginning to take over as it was designed for the second line of defense, but unfortunately it's becoming the first line of defense now. We need to think about in long-term corrosion effects, because we don't want to lose our infrastructure, whether it's going to transport oil and gas, or it's going to transport newer products such as hydrogen, or even moving our packages, our Amazon packages, or our mail through the pipelines. These pipelines are not going to go away. They're going to be used for other uses. as the industry changes. And these are the kind of things we need to look at. We also need to look at what is the true design life of that structure. We have structures in there over 100 years. We need to look at what we're putting in today. Are the pipelines of today going to last 100 years? Are we going to move that way? And these are the kind of things we need to look at. We also need to look at the encroachment of people around these structures, safety, integrity we need to maintain the integrity. And then we need to look at all of the factors that are involved. When we bring the engineers together in the design, we need to look at the stresses. We need to look at the loading. We need to look at the environment that's around the pipe, and then finally the integrity of the pipe and how long it's going to last. And these are the performance or KPIs, key indicators that need to be maintained throughout the life cycle of a pipeline. And this is where the company I'm doing work for. This is the kind of work that we're doing with our GIS systems, with data management, and the calculations that I just talked about. So, thank you.
In the video description, I will have the LinkedIn profile for those who want to connect with Joe, but also I'll have his contact information as well if you'd like to further have a discussion with him on this topic or any other topic. Joe, I want to thank you for having the opportunity to talk with you today.
Well, thank you, Jim. I appreciate it, and I'm looking forward to some future discussions where we could get into specificity of any one of these topics that you think is important to your viewers. Okay.
Definitely. I think you've covered a lot that needs further unpacking. Hey, have a great day.
Thank you. Appreciate it.